Hi, welcome to another edition of Ordinary Differential Equations. Today we are going to talk about some advanced issues related to step functions. Let's go ahead and see how this looks like. So you remember we talked about step functions. The basic step function, we wrote it as u sub t, u sub c of t. This was defined to be 1 for all times less than c, and it is 0 for all times larger than c. C is a positive number that indicates the time at which a signal is converting from 0 to 1. So a signal staying at 0 level until time c, at which it jumps to 1 and then continues at that level. Okay, we said that this is a kind of a basis function out of which we create a lot of discontinuous forcing functions. They are of major applications in engineering. Anything that comes with a switch has this kind of look. Let's go ahead and look at a simple problem. Suppose the question is graph say g of t is equal to say 1 u1 of t plus 2 u3 of t, and then say minus 6 u4 of t. There are many different ways of approaching this problem, and I advise you to try to do it in all those styles to become comfortable in converting your answers, your approaches from one type to the other type. So one way, essentially, you just talk it out and you're going to get the correct graph, at least in very simple situation. So what does u1 of t means this c is 1, u3 means this c is 3, and u4 means this c is 4. So these are three separate switches. Each of them is being activated at some different time. And then we have these multiples. These are like voltages that are being added to whatever we had before. So 1 u1 of t simply means a signal that up to time 1 was 0, and at time 1 it became 1. And then at time 3, so up to time 3, nothing is happening until a new switch is turned on, and at that time a signal with the amplitude of 2 is added to whatever we had before. So this is 1 more and this is 2 more. So at u3 we have this. At time 3 we have this signal. This signal keeps marching forward until time 4. At time 4, which has happened here, we are drawing out say 6 volts or dropping our signal strength by 6. So by the time we reach to time 4, we are falling down by 6. So this was this 1 is this 2 is this one, and then minus 6 is this drop here, minus 6. So we're going up here and up here and dropping here. When we get to this point, then we are going to continue at that level. There are no more switches, so the values of the functions goes from 1 to 3 to minus 3. Okay, this problem is simple enough that, as we said, we just talk it out due to the fact that these are all constants. There isn't really any complication to worry about. But let's go ahead and do it another way. So I say g of t. So our time breaks are at time 1, 3, and 4. So t less than 1, and then t larger than 1 and 3, and t between 1 and 3, then we have between 3 and 4, and then we have t larger than 4. So So t less than 1, nothing is on, so that is where all quiet. Between time 1 and 3 we have only this active, and that one is not there yet, so our function is just 1. From 3 to 4, that is after time 3, but before we hit 4, both of these switches are on, but that one is as yet not active. After time equal to 4 seconds, we have all switches on, and our function is 1 plus 2 minus 6. Well, of course, this is just 1, that is just 3, and that's just minus 3, that is what these values are, 1, 3, and minus 3. So you can always take your times at which the function breaks, make a table of values for time, make a piecewise defined function, figure out what the values are on each of these domains, and graph your function. Another way of approaching this thing is using our trusty Desmos function, and it's very important to learn some of the software for us to be able to handle more complicated problems later on. Let's go ahead and see what do I have here for you. Let's maybe look at something easier first. First of all, how do we define a piecewise defined function on Desmos? The notation is a little bit different from what we had for functions. Essentially, you're packing several different functions into one. So this is how it's written. So this is u of t. This is like grandfather of all the step functions. T less than 0, it is 0, and t larger than 0, it is 1. So it looks like the graph that we have here. It's a function that is 0 here, and then it jumps and becomes 1, and then goes on. The jump happens at time 0. Now we have a bit of an issue here, that the notation that the textbook uses for u sub c of t, we cannot use that all that easily in Desmos. So instead of doing that, we do a much cleaner approach, which is the shifting function. Suppose I want this switch to happen at, say, time 3. So let's make another function. I call it, say, z of t. If I want to push the jump 3 seconds forward, what I want to do is to take my step function and write u of t minus 3. So what that does is that the red curve just got pushed forward by 3 seconds. Now that's where it is, and the jump is happening at time 3. So instead of writing u sub 3 of t to get a step function that jumps at time 3, we are going to define a basic step function whose jump is at time 0, and then adjust that by shifting so that it will go and jump where we want to actually jump to happen. This is actually a clean notation. Okay, now that we understood what this is gonna do, let's go back to our basic step function. The one that we just did by hand here, we just bring it back up to you. 1u of 1 of t plus 2u 3 of t minus 6u 4 of t. Let me see if you can go ahead and reproduce this on step function by yourself. How would I do that on Desmos? What would I do? So take a short break, or long break, figure that out by yourself. Try to remember what I just typed there to get the basic step function. By the way, some information about this is on my website. Look for hints for Desmos, and you will see lots of interesting additional information there you can use. It's really nice software. Okay, so the idea is that you try to do this thing yourself. Now let's go ahead and so what do I have here? That's f of t, or maybe my example was called g of t, whatever it was. It was 1. If you want to see the 1, it doesn't make any difference. 1 of u1. You remember now we said instead of u1 you write u of t minus 1. 2 of u2, instead of u sub 2 we write u of t minus 2, so that pushes it by 2 seconds. Then minus 6 u of t minus 4. That would be how to type in that function. Now let's go ahead and see what that one looks like. Okay, now in Desmos you don't see those vertical lines. It simply is not a function to go vertically up, so Desmos just jumps straight from this point to that point. What happens exactly at the point of the jump, we are not going to concern ourselves with that. Actually, it's a major engineering question. How do you actually jump from one value to another? Lots of engineering questions do come up. Mathematical questions also do come up, but they are all beyond the scope of this class. So next time you take your circle class, you will for sure deal with the issue of well, how do you actually jump from one number to another number? Here's another example, a little bit more sophisticated. H of t here, lengthier, more sophisticated. Let's go try to practice it by hand, and then we come back and then see how to actually do that here. Well, on Desmos it's going to be very easy because everything's being done for you, but how about doing it by hand? Let's so our next question here is, suppose I have say g of t is equal to t minus 1 u sub 1 minus 2 times t minus 2 u sub 2 plus say t minus 3 u sub 3. And the question again is, well, what's the graph of this? What's the complication here? The complication is simply that our voltages that are being added with the additional of any switch is variable in time. So here they were all constants, so we didn't have that much of a hard time going up and down. This one, however, is going to give us a little bit of extra challenge. So how to handle this? We can talk it out, but perhaps it's a lot safer to go after this approach and then graph that. So say, let's see, g of t. What are my time breaks? 1, 2, and 3. So I am figuring out what is before 1 second, between 1 and 2 seconds, between 2 and 3 seconds, and after 3 seconds. So before 1 second, I don't have a leading term here. For example, if I had a t or something, I would have had that. But right now, the term before this is just 0. So that makes it just that much easier. Some other problems, you might have some expression here, and then, well, you'll have that expression here. Between 1 and 2 seconds, between 1 and 2 means this became active, but that one isn't. And of course, this one isn't. So this is the only thing that is going. So you have the value of function is just t minus 1. Between 2 and 3 seconds, 2 switches are on. The first one brought in, you say, a voltage that is growing as t minus 1. The second one is a draw of 2 times t minus 2. After time 3, all switches are on, and so you have t minus 1 minus 2 times t minus 2 plus t minus 3. So this is t minus 1. This becomes t minus 2t, so that becomes minus t, and then I have minus plus 4, so it becomes plus 3. This one, let's all write it out so that I don't make a mistake. Let's see, I have t minus 1, then minus 2t plus 4, and then t minus 3. Is that right? So what happens? So of course, what happened here, it looks like my t's cancel, and then it looks like everything actually cancels, and all I'm left with is nothing is left, it's just 0. So this is a function that before 1 second is 0, from 1 to 2 is t minus 1, from 2 to 3 is minus t plus 3, after 3 is just 0. Now we are ready to actually graph this thing. So it's okay, let's graph this. Okay, so what do we say? Let's go ahead. Maybe I make 1 second here, say 2 seconds here, 3 seconds here. Before 1 second, nothing's going on. From 1 to 2, I have the function t minus 1. So if you wish, you want to perhaps ignore everything and just graph t minus 1. So that's a basic question from psychology algebra. T minus 1, straight line. It has a y-intercept minus 1, x-intercept of 1, and it goes like this. Okay, that's a graph of t minus 1. But of course, not the whole graph is relevant to us, only applicable from 1 to 2. So this is the only section of it that really applies. So this section is not really part of the answer, because for times below lower than 1 we were at 0. So so far we are going at 0 and then going up. The rest of this thing doesn't apply either, but I just drew it so that you see the whole picture. Then from 2 to 3 seconds, that is from here to here, we have a graph of minus t plus 3. Well, what does that one look like? Minus t plus 3, well, that's another straight line. Its y-intercept is 3, slope is minus 1, so say 1, 2, 3, or let's see, well, maybe a bit bigger than that. This is 1, let me clean it up a bit. This is 1 and 2 and 3. Sorry, I have to go up here. So it's a graph that comes like this. Okay, so this is the graph of minus t plus 3. But again, is the whole thing relevant to us? No, it's only relevant from 2 to 3, and it's this piece of this picture that's part of our puzzle. The rest of it, I just drew it so that I see where the whole thing is. After time 3, it's very easy, it's just 0. So our picture goes like this. So we see that this graph is like a blip, like a little mountain or something. A very kind of weird looking formula for a little mountain. So we it took us a bit of time to do this, and you can realize what's going to happen if these functions become more and more complicated and these times become all sorts of numbers. We are actually facing a bit of a challenge. So let's go see if Desmos gonna do this thing for us. So I have this function h of t, everything you saw there, I have typed it here. Again, remember, this is just u1. The way we type that is u of t minus 1, and so on. So let's go ahead. Clicking here activates the graphing. You see that little blip showed up. That is the So if you want to unactivate that, deactivate the grandfather formula. So this is the graph of that function. Maybe I better perhaps looking too tiny on your picture on your end. Let's make it respectable. Okay, so once you're here, you can input any function you want here and so on, and then you get all sorts of problems. So perhaps if you have time, we come back and look at some more advanced examples. But let's go ahead. Important thing is to learn how to draw this thing by hand. Reason your way through, and then at the end, go ahead, use that software to make sure you were right. Don't jump into using software right away because, well, there is a version of a couch potato which applies to a scientist that relies on a computer all the time. You gradually lose your own senses of numbers and such, so you don't want to every time reach for a remote and have it done for you. You want to try to do it yourself so that you stay current with what is happening. And sometimes computers go wrong, and because the programmer made a mistake, or perhaps some sort of weird thing happened inside the hardware and such. All of these kind of things have happened in the past. You do come across glitches. Those are not things to be just dismissed. So it is important for at least some of you guys to be able to reason your way without relying on a computer too much. Okay, sometimes our problems are expressed in reverse direction. What do we mean reverse direction? Well, sometimes it's written in U notation and we go piecewise defined, but sometimes it is given to you in a piecewise defined, and then you want to go back to that style. Let's just go ahead and practice that. So I'm going to just make up some functions, say f of t, say this is t for t less than, let's say 2t for t less than 3 seconds, and then it is t squared for t between 3 and say 5 seconds, and say it is t cubed for t between 5 and say 8 seconds, and say it is 1 for t after 8 seconds. So lots of pieces here. So this is a piecewise defined function. Typically that's how many problems start. They say, okay, we have an external force that looks like, say, like this, and then you want to convert it to U notation so that you will be able to actually use step function in your problems and do the differential equations with this type of forcing function. So how do we go approach this problem? Say I'll say, excuse me, f of t. Okay, this one, unlike all the previous ones, this does start with something. So if it starts with something, well, you want to start with that. And then we have our break times 3, 5, and 8. So I write my first switch. What does that switch do? At time 3. Think about it like this. At time 3, we are as if we are turning this one on and turning that one off. So easy way to explain it is you are taking what is being turned on, and that is no longer applicable, so you can think about it as being taken off. And then you repeat U sub 5. At time 5, it is as if you are turning on t cubed and turning off t squared. So it's just like t cubed minus t squared, and so on, so forth. You go U8. So at U8, your signal turns into 1 for all times, and whatever was there in the previous stage, that is being taken off. So that is how to convert from, so we might call this problem convert to step function or U notation. And of course, if you want to graph it, it's your choice. You can use the notation of piecewise defined functions in Desmos and do it that way. However, you have this one also available to you, and you can do it that style. Either one will give you the same answer. Okay, now let's go ahead, tie our problems to problems in Laplace Transform. So suppose I have a function, let's call it, say, f of t, and it is 0 for time less than let's say 3 seconds, and then it is t minus 3 for t between 3 and say 6 seconds, and say it is 0 for time t larger than 6 seconds. Okay, kind of a simple step function. Question here, what is Laplace transform of f of t? So before we do that, how would that come up? Suppose the right hand side of a differential equation, or the external forcing term, is such a thing that up to 3 seconds there is no external force. From 3 to 6 seconds the external force is t minus 3, and at 6 seconds it's all cut off. We are back to 0. So it's like we are like that problem of a spring and a pan attached to it, and then you're adding something. At time 3 you are starting to pour in some sand maybe, and it's just piling up something here while this is going through its motion. And at time 6 you get a leaf blower and just blow the whole sand away, and there is nothing there at all. Or you just disconnect this thing and all the sand is poured out. There is no additional external force. Well, if you want to study the oscillation of such a system, you would need to take the Laplace transform of that to see what happens. So how do we approach this? Of course, our basic formula is the following. We have the following formula: Laplace transform of u c of t. Do you remember what that was? U c of t, exponential of minus cs over s. Okay, make sure you remind yourself, add it to your table, and so on. So if I want to use this formula, if I do not want to reinvent the wheel about integration for this, then I'm forced to take this and write it in the step function notation to be able to make use of that. So you see that this problem naturally pushes you to do this, and then you are ready to actually apply the integration or the Laplace transform. So I go ahead and say, okay, let's go ahead and rewrite my f of t. So at the beginning, well, nothing is going on here. Then we have a switch at time 3, so I write u3. So what is turned on? Well, I'm turning on t minus 3. What is turned off? Well, there wasn't anything to be turned off, but if you want to insist, you're turning off 0. So let's minus 0. Then at time 6 we have another event. Think about it as if you're turning on 0. That means nothing. Minus whatever you had before is being taken out of the table. So let's clean this up. So it's f of t is equal to t minus 3 u3, and then this one I can write it minus t minus 3 u6. Okay, now we are going to be facing another challenge, which is, okay, this I have a formula for its Laplace transform. Let me remind everybody what we had. If you had Laplace transform, if you have some function g of t, and then we said you delay it by c seconds and switch it on at that time, then Laplace transform, it would be the Laplace transform of the original function that was g times exponential of minus cs. Okay, one thing we emphasized quite a bit before is that the delay and the switch time have to match for this formula to work. Well, we are lucky here that it is indeed so. So if I have Laplace transform of this is u3 of t times t minus 3, then what I do is that I take like for a second, ignore the step function, ignore this delay, just focus on that function, in this case t. Remember what was the Laplace transform of that. So remember Laplace transform of t to the n, what was that? It was n factorial over s to power of n plus 1, or specifically Laplace transform of t 1 factorial over s2. So for t, Laplace transform is 1 over s2. For this switch and delay, a factor of exponential of minus whatever this switch and delay is, 3s times 1 over s squared. That will do the problem. So Laplace transform of this portion is all easy. The question is, what do I do for the second portion? Laplace transform of u6 of t times t minus 3. Okay, this is gonna be one slightly tricky question that shows up in some of your exercises, shows up in practice actually. What do I do? Well, what is the problem? Well, the problem is that this is my switch time, this is my delay time. They have to be same for me to apply the formula. And there, here obviously is quite loud that they are not the same. Well, you have to apply. Let me see if you can come up with a solution. You have to think about it. What would we do? Some sort of a perhaps maybe, if you cannot think of something, let me remind you of some basic tricks in algebra you had back in high school. Add and subtract stuff that you were used to do. So some basic algebra tricks or trigonometric tricks and such have to be applied for cases where the switch and delay are not matching, to figure out the way of forcing them to match. So what do we do? How do you force them? Well, this is the essential thing to go with. We cannot tamper with the switch time. So I leave the switch time as it is. At time 6 something happens, well, I leave it here. This means a delay of 3. I want a delay of 6. How can I artificially put a delay of 6? Well, subtract 6, and of course, well, you know we are off. Well, then put back what you have borrowed, 3. So I have to write t minus 6 plus 3 so that it will be same as t minus 3. And then what? Well, this is same as Laplace transform of u6 of t times t minus 6 plus 3 u6 of t. Okay, now we can apply linearity of Laplace transform. Say, okay, this is a kind of creature I can make peace with. This is fine because this 6 and that 6 match. I know what to do with that. This factor of 3, due to the fact that there is no time issue with it, I can just pull it out, and then I have just Laplace transform of u6 of t by itself, and there is no issue of matching some delayed function to some switch function. There is just switch u6 by itself. And then so here I will have exponential of minus 6s over s squared. So that's all set there. And then here I have 3 times exponential of minus 6s. Laplace transform of that by itself was this. So all put together we have the following. The first expression, exponential of minus 3s over s squared plus exponential of minus 6s over s squared, and then 3 times exponential of minus 6s over s. Now this is s, that is s squared. If you want to take a common denominator, be my guest. More often than not, not much is going to come out of that. You have to kind of be using your algebra skills to see if, well, should I simplify or not. And well, that all depends on the problem that you are looking at that particular moment. So that is one issue that is slightly off the beaten path, but it is significant in applications. It does come up. We have to be prepared for it because so let me remind you one more time. Laplace transform of u c of t f of t minus c, that was exponential of minus cs, we did derive this, times f of s, but this relies on the fact that you turn on the switch at the same time that equals to your delay in your function. Otherwise, no. Let's go look at another example where it is not so clear what we are supposed to do. Let's see, we have time maybe for one more thing. Let's take a function f of t, which is again at the beginning is just 0 all the way up to say 1 second, and then there is this and the question again as before is, what's the Laplace transform of this function? Well, we learned the approach. First write it in the U notation, then apply that, and if doesn't apply directly, adjust this to force it to match to that. So f of t at the beginning 0, at time 1, so I have u1 is the only thing that applies here at time 1. This is coming into the system, and I have to write minus 0, which doesn't change anything, so I don't even write it. So that is what it is. Now I want to take a Laplace transform of this. I'm taking Laplace transform of t squared minus 2t plus 2 times u1 of t Okay, what do we do? Here's a problem. I need my function here to have visibly a delay of 1 second in it from something that shows up in my table. What is that? So here I want to force this thing to have t minus 1 in it. So I have t squared minus 2t plus 2. Now this is a very simple problem. If you notice that you can do completion of squares here and the problem will be done, but that's a bit of too much of a simplistic view on this. Wouldn't work like that for a more complicated problem. So what do? We have to adjust each of our t presents by the trick that we did before. I forcefully bring a delay of 1, but then I have to compensate for it. So t minus 1 plus 1 is just t, and then I'm squaring it. Minus 2 times t minus 1 plus 1, well, that is this t for it. And then I have a factor of 2. Now if you wish, call this thing something so that you don't get tempted to just add the 1 back into it and mess up what you worked so hard to create. So this is, let's call this thing w, so we don't destroy what we create. Let's call it w plus 1 squared minus 2 times w plus 1. So we did a substitution of t minus the switch time, call it something else, Now go through the algebra that you need, that is w squared plus 2w plus 1 minus 2w minus 2, which is this, plus 2. Well, let's go ahead, clean up. It so happens here accidentally you do have a lot of cancellation, but that's not normal. W squared plus 1. Now go back, remember w was t minus 1. It's t minus 1 squared plus 1. So let's restate the problem we had at the beginning. This peculiar polynomial is same as this delay adjusted polynomial. This is same as that. Of course, in this simple problem you could see that right off the bat, but in some other problems it's not all that obvious. Then this becomes, now instead of that you write t minus 1 squared plus 1, all of that times u sub 1, and then you say, well, let's break it up into pieces. T minus 1 squared times u1 plus 1 times u1, well, that is just u1. Well, now this switch and this delay do match. I go and look, what was the Laplace transform of t squared? Well, that was 2 factorial over s cubed. You remember that? Then presence of switch and delay creates this multiple. Well, it's not a c, it's just 1. 1s is just s. And then a Laplace transform of u1 itself, which is just exponential of minus s over s. So to make it clean, exponential of minus s, we can factor it out, 2 over s squared plus 1 over s. And usually taking common denominators and such in these problems, it's expenditure of time that may not pay. Okay, so this kind of approach can be used in a variety of cases. At the end, you have to see what you know. In here was just straightforward algebra. Sometimes it's trigonometry, sometimes the properties of exponentials and so on. Apply whatever is reasonable, and then your problem can be done easily. Okay, thank you for attending this lecture. There will be some exercises on this. Good luck and God bless until the next meeting.